Physics students, hello. Physics aficionados, good day to you. We're going to talk, this is going to be the first in a couple of videos about gravitation at maybe what we can call astronomical scale, and that'll feed into orbits in an upcoming video. So, we're going to start saying there's an object M located at position R, or a mass, little m, located at position R. R is a vector that defines the position of an object, in this case little m, relative to this place, the center of, let's call it a planet with mass big M. Alright, so notice here's a vector R that defines the location. So let's talk about what little m weighs. Well, there's a couple ways to say that, but what I usually say is, well, what does an object weigh? That depends. What an object weighs, well, that is gravitational force. Here is a depiction of that gravitational force. That depends on a couple of things. How much does an object weigh? Well, it depends. What is its mass? And what's the strength of the gravitational field that it's in? Now, when I say little m, I do mean this little m. And when I say g, I mean the gravitational field made by mass big M. So, okay, that's kind of it. Well, how big is that field? How big is capital M's field? How strong is capital M's field at a distance r from its center? Well, depending on how you want to, it's kind of a chicken and egg thing, but what we can say is that there is a gravitational field made by M. The nature of mass, or the gravitational nature of mass, is that what masses do is create gravitational field in the space around them. What masses do also is experience the effect, which is to say the force, or a force, that is exerted by a gravitational field that they're placed in. So that's what's called the gravitational nature of mass. All right, masses by their nature create gravitational fields. Masses by their nature are have forces exerted on them by gravitational fields. And the field that an object makes, by definition, we can say, how strong is a gravitational field? Well, that depends. It depends on the magnitude of the mass that makes the field. It depends on how far from that mass's center you are, in particular the square of that distance. And in order to make the numbers work out right and the units work out right, we put the big G, which is called the universal gravitational constant, in there. G, not negative, 6.67 times 10 to the negative 11th, happens to be in Newton meters squared per kilogram squared. And, well, that makes G have the right units to match up with what we'd expect here, and those are newtons per kilogram. All right, so we can say that G is a measure of the gravitational force per unit mass placed in a field, measured in newtons per kilogram. Solving for, well, I guess analyzing the units of little g from this expression will yield those same units. All right, and thus, if we say that this gravitational force exerted on mass little m is little m times this gravitational field, then that gives us what we're used to, perhaps, some of us, as Newton's law of universal gravitation. Notice, only big M here. Here we have both M and little m. Okay, if we want to be explicit about this, both G and force, field and force, are both vectors. By definition, they both point in what's called the r hat direction. The r hat direction, this is called a unit vector. And that just means direction. And the r hat direction is radially away from the center of an object. Or from a point, I should say. radially away from a point, but fields and forces both point toward objects, toward the center of objects. So to make that a true vector equation, we say that those fields and forces both point in the negative r hat direction. Okay. Now, and objects or object m's, I'm talking about little m's, acceleration at location r. And this doesn't matter if the object somehow is suddenly is placed there at rest or is floating by there and experiences only force Fg. Well, the acceleration can only be expressed using Newton's second law, net F equals ma. And the force exerted on this object is Fg equals ma. And Fg we can write in one of two ways, but I'm going to write it as how we started, which is to say m times g is m times a. And what we're used to doing is just saying zip, zip, same m, okay, good, except it's worth pointing out some intricacy here. All right, and that intricacy is that we're talking about two different aspects of mass, two different aspects of the nature of mass. All right, so the nature of mass, maybe I'll sidebar here, nature of mass, is that mass does two things. Masses create, experience force by gravitational field. We call that gravitational mass. All right, there is an idea called gravitational mass, and so I'm going to put a little g here to indicate that because we're talking about the fact that there's a gravitational force on this mass, that comes from the fact that part of the nature of mass is that it experiences a force when placed in a gravitational field. Well, the other inherent nature of mass is that mass resists acceleration. And we call that inertial mass. And that lives here, right? To say that, for Newton's second law, to say that an object's acceleration is inversely proportional to its mass says inherently that masses resist acceleration. The larger an object's mass, controlling for net force, of course, the smaller its acceleration. All right? So this is what can be referred to as inertial mass. The fact that objects are hard to accelerate, or to varying degrees hard to accelerate, has nothing to do with the fact that they create gravitational fields. It has nothing to do with the fact that they are pushed or pulled on by gravitational fields. So those aren't the same thing, except, oh, I put the I in the wrong place. You probably noticed that. The inertial part goes here by mass, inertial mass. Those aren't really the same idea, except they are. They aren't in that they're inherently different phenomena, but what we can see is that in this room, if you take any objects, any two objects, regardless of their mass, and we drop them, well, their accelerations are the same thing. All right? Galileo's been doing that, or not has been, but was doing that, 500 years ago-ish. All right? So when we say, and it's okay to do, that, yeah, these are equivalent, saying they're equivalent isn't the same thing as saying mass is mass, m and m are the same thing. I mean, they are the same thing because experimentally people have gone to great lengths to prove that gravitational mass and inertial mass are equivalent, but they're certainly not the same idea. All right? That's way more, or at least it's something more than a lot of physics students really need to worry about, but it's neat to talk about. That mass isn't just, a letter. It has two very different fundamental ideas. But again, we can take two objects of any different mass and drop them in the same gravitational field, and they will have the exact same acceleration. And again, that yields some truth to the fact that gravitational mass and inertial mass are actually equivalent. All right? And so, if we know what the strength of a gravitational field that an object is in, we know how fast the object will accelerate. All right, and this also is a reason for the fact that, look, if we look here, right, gravitational field on the left measured in newtons per kilogram. Acceleration, as many of us know, measured in meters per second squared. And then, well, we say, yes, fine, that's true, because a newton is a kilogram meter per second squared. Yeah, it is because we say it is, because people, guess what, not for the eternity of the universe, but since Newton, well, probably since well after Newton, but decided to say, let's define this unit called the Newton, where it allows us to say that gravitational mass and inertial mass are the same thing. Okay? Okay. Anyway, where the rubber meets the road for a lot of us, we can say this, that acceleration and field aren't the same thing, but they are numerically equivalent. Okay? One yields the other. Okay. So that's a straight up sort of gravity situation. Here's a gravity kind of question where we can do these with what are called kinematics equations. We can do these problems with very little difficulty, where we say let's drop an object and it goes some distance. How fast is it going? But things get quite different when we get to the astronomical scale. All right, and that's because what I've done here actually is on purpose made. Notice here's R naught and here's R. And what I'm saying is that an object starts at some distance and ends up from the center of big M. It ends up at a distance half as far away. So I'm defining that the magnitude of R is half the magnitude of R naught. And what that means is if there's a field here, let's take and say anywhere at that distance from the center of this object, there's a field. I'll write it as G naught. And when we get half the distance to the center of this object, because G is G M over R squared, when we get half as far away, R gets 2 times smaller, G gets 2 squared times bigger. The field here is 4 G naught, which means this object does not have a constant acceleration, and therefore kinematics equations to say something like v squared is v naught squared plus 2a delta x, that doesn't work. That doesn't hold up. That only works if a is constant. A is not constant. A is not constant because field's not constant. So we can't use, quote, kinematics. But we can do two different approaches depending on your level of comfort with calculus. All right, so I'm going to do I'm going to do some calculus that derives an expression for something important. Regardless of how you solve this question, you're going to need an expression, and that expression doesn't come from nowhere. So if you're a calculus-based physics student, you will either recognize this or this will be of some value to you at some point. If you're not a calculus student, you can skip ahead or just buckle up. So, how do we want to find the speed of this object of mass m, when it gets here? We're looking for this speed v. Method 1, let's call it. The system we're going to define is m. And what that means is there is a gravitational force exerted, I'm going to do this, watch, on m by big M is what's called an external force. And what I mean by that is, since our system is comprised only of mass m, and mass big M is not part of that system, a force applied by it is a force applied by something outside of our system. Thus, that's called an external force. And we can then say that the work done by this external force is equivalent to that object's change in kinetic energy. Now, the object M can only have one kind of energy, and that is kinetic energy. The object, little m, cannot have gravitational potential energy. A single object can never have gravitational potential energy. Two object systems can. This is not a two object system. This is a single object. So the only thing that this work done by this external force can do, work always changes energy of some form. Our mass, little m, can only have kinetic energy. Thus, the work done can only change this object's kinetic energy, and the work is equivalent to that change. So, how much work is done? Now, we can certainly say this. That's K final minus K initial. Notice we said released from rest, so that's going to go away. So as long as we can find the work done, we can set that equal to 1/2 mv final squared. That's going to be true. So how do you do the work done? Well, work done is, in a simple sort of F times delta x, right? Really, it's F dot delta x. Well, that's if the force is constant. Or we could even, if we knew what the average force was, we could use the average force over delta x. But this force doesn't change uniformly over space. So what we have to do, here comes the calculus, is we have to say there are lots of little amounts of work done. And the integral part means we've got to add all those up to figure out the total amount of work done. Well, there's a little tiny amount of work done, say, as the object goes from here to here. That's a little tiny dl, or dl. dl means a little tiny length. And what there is in that tiny little dl, there's a pretty constant gravitational force. All right, dot dl. dl is actually a vector. In this case, it points like that. Okay, so what we've got to do is we can say that the work done, I'm going to jump up here now, the work done is the integral of, well, fg, that's, remember, negative g m over r squared r hat dot dl. So, granted, for this, you need to be brushed up pretty good on some vector operation sort of stuff and calculus. Okay, now the r hat dot dl, what that's going to yield, r hat is a unit vector, so it has a magnitude of 1. It just means direction, and this means a vector that points in a little vector that points in a certain direction. So what we have is this yields, this is the same thing as g m over r squared scalar dr. All right, the dot product of two vectors, this is r hat dot dl. The dot product of two vectors gives us a scalar. In this case, it gives us the scalar dr. All right, now, we are going from r naught to r. That's going to yield, when we integrate this, we have, first of all, this negative. When we integrate gmm over, well, I'll do this, watch, gmm integral 1 over r squared dr. That is that the work is negative g, and from r naught to r. Negative g, big M, little m. That's integral r to the negative 2, and that's negative r to the negative 1. So here's the negative 1, here's the negative r. You okay there? And instead of calling these r, I'm going to call them x, because I did that in the diagram. So this goes from x naught to x. From x naught to x, which means I have to evaluate from x naught to x. Okay, so that means that our work done is, how about this? Well, okay, fine. It's g m m over x minus g m m over x naught. And from here, x naught is twice as far away as x. So this is gmm over x minus gmm over 2x. Right? And that work done is g big M little m over 2x. We get something minus a half of that something, and that's half of that something. Now that equals, remember, that work done equals the change in kinetic energy of this object. We said the object starts at rest, so K initial is gone. All right, so we can set this equal to 1/2 little m v squared. We get a 1/2 on both sides here. We get a little m on both sides here. And we get our expression for v, which is g m over x. Fair enough? Okay. Now, the other way to do this, I'll come back to that. The other way to do this is to say that our system is little m and big M. And if we do that, what we have is a system where objects exert forces on each other. Those forces are gravitational forces, and only gravitational forces, right? There's an Fg like this, there's an Fg like that. And gravitational forces are conservative, and thus this system's mechanical energy is conserved. We can say that the system's initial kinetic energy plus the system's initial gravitational potential energy is equal to the sum of those final values. Right? We've also said that the system starts, or there's no motion of objects relative to each other initially, so that goes. And now we need an expression for UG initial. Or, well, actually, we need an expression for UG, for gravitational potential energy, as a function of position. All right? So that's what this slide's for. Here's an object, big M. Here's little m. And little m, let's say, goes in some path from here to there. All right, this is position A. This is position B, if you like. All right. What we know is that at any place on this path, say right here, here's the object, there's a force Fg like that, right? And in particular, let's say there's that force as this object travels along a little tiny dl vector. All right. Now, gravitational forces are conservative, and by definition, conservative forces have to yield or have to obey the following relationship, and that is the work done by a conservative force is equal to negative delta U. So that's a definitional aspect of what it means for a force to be conservative. That when that force does work, the result of that work is that an object's potential energy decreases if the force does positive work. And the amount of decrease of potential energy is equivalent to the work done by the force. All right, so in our little dl here, in our little tiny distance, there's a little tiny change in system gravitational potential energy, and that's equal to, well, that's equal to the negative of the tiny little bit amount of work done, sorry, by the conservative force. So I'm going to say there's a little tiny change in potential energy, and that's equal to the negative of the little tiny bit amount of work done. All right, the little tiny amount of work done, there's the same negative, is F dot dl. All right, so now I can say that, excuse me, that integral does not go there. Sure. And then if I want a function for u as a function of r, what I can do is integrate all of these things. And I can say that u as a function of r is negative fg dot dl, or is negative g mm over r squared r hat dot dl. Right? This negative from the definition. This negative from saying gravitational force points radially inward. All right, so these two negatives, thank you very much, are gone. From before, this r hat dot dl, it's a dot product of two vectors, one of which has a magnitude 1 and no direction, and dl is a little tiny vector that points in a direction along that path. That yields us a little tiny radial distance. Okay, so our potential energy as a function of r, this is gravitational potential energy as a function of r, is the integral g mm over r squared dr. That means that u of r is negative g mm over r, because we're integrating r to the negative 2 dr. That gives us negative r to the negative 1, or negative 1 over r. Now what we don't have here is the fact that this is an indefinite integral. Nothing here, nothing here. We need a constant of integration. And then what we define, what we agree to as scientists, is we say, let it thus be stipulated that when r equals infinity, when things are infinitely far away, the two-object system has no potential energy. And what we're saying is, if you move things far enough apart, there's infinitely far apart, the field that each of them is in is infinitely weak, and therefore that field can exert no force and do no work and change no energy. So when things are infinitely far away, there is no potential energy. So when r is infinity, that means this gets really big, then this gets to be 0. Well, when r gets really big, when r approaches infinity, this does approach 0. Okay, so when this approaches 0, this approaches 0. That means that c is irrelevant. C is 0. So that defines for us something that maybe some of you have seen before, that gravitational potential energy as a function of r, by definition, goes g product of masses over a single factor of r. That negative doesn't mean inward. It's not a vector. Gravitational potential energy is not a vector, it's a scalar. The negative means it's negative. And what that means is gravitational potential energy, UG, as a function of r, is a negative inverse curve, which means it looks like that. Which means, this is weird, as r gets bigger and bigger and bigger and bigger and bigger, where things get farther and farther and farther away, well, this means, look, at this one, there's that much gravitational potential energy. Farther away, there's this. This is more. This is more UG as we go up that y-axis. We get more gravitational potential energy as things get farther and farther apart, up to a UG max of 0. So the negative here allows us to say that as things get farther apart, and take that in the scale of this room, right? Take an object, lift it up. Sure, there's more gravitational potential energy. It's getting farther away from Earth's center. But the most the object could have, if we kept lifting it up forever, the most gravitational potential energy the Earth mass system can have is nothing. That's what that negative means. Okay, that allows us to agree on an expression for gravitational potential energy, and that allows us to proceed a little farther here. So what we can say is that initially there is a gravitational potential energy Gm over, I'm going to go right for it, 2x, right? X naught is 2x, right? This distance x, this distance 2x, equals 1/2, this is little m, v final squared, whoops, minus g m over x. We want to solve for v. Let's add this term to both sides, and we get g m over x minus gmm over 2x equals 1/2 mv final squared. Whether or not you know it, we are already at the same exact place we were here. We're doing the same thing. Because notice, look, we did this. We integrated. We found the potential energy function. We set it equal to the kinetic energy. We just did that in a different approach. All right, look, we got a factor of little m in every term. This side does yield g big M over 2x equals 1/2 v final squared. We can take a half or multiply both sides by 2, and we get that Vf is Gm over x. Gm over x. Okay, so it's likely, if you're in a first-year course, first-year physics course, an algebra-based course, someone has told you that okay, this is that Ug is negative GMM over R. Do it, use it. Okay, we've gone to some pretty great lengths here to show that that is true and define why it's true. Perhaps you had to take this with a grain of salt, but okay, you know, eventually we, yeah, okay, you got to take something with a grain of salt. I'm not asking you that. I'm not saying that's wildly unknowable. It's, you know, that one's not too bad to wrap your head around when you read on it a little bit. So we've gone to some lengths to derive the expression for gravitational potential energy, and/or we've gone to some lengths to derive a proper expression for how much work is done when a force is non-constant, or even when a force varies in a non-constant way. So no matter what, to do this right, without taking for a grain of salt or accepting on face value that this is the case, you've got to employ some calculus to do this in a thorough manner. Okay? Once you do that and can accept that this is the case, I would say for sure that this is the way to go. Why do the calculus if someone will tell you it's okay to use that? All right, it's great to see that the calculus yields the same result regardless of approach. I love showing where two different approaches involving definitions of two different systems will yield the same result. I call that darn good physics. All right, my people, if you're not bleeding from the ears yet, listen to me next time.